Okay, welcome back to some more lecture material for Chapter 2 for Chem 161, where we'll be discussing some further details on isotopes and the calculation of average atomic mass. As we saw in a previous video, we had the concept of the isotope, and so we'll just touch on that again here briefly. An isotope is, of course, an atom that is of same type to another atom governed by the number of protons. So we're going to see the same number of protons in the nucleus. So we'll say atoms with same number of protons, P plus, but differing by the number of neutrons, N. Okay, so as an example, you might see carbon 12, and we'd expect that the carbon 12 with 6 protons could be elaborated, and we could list the total number of protons as being equal to 6. The number of neutrons would therefore be 12 minus 6, which of course is 6. And we know if this is a neutral atom under consideration, that the number of electrons in this atom would have to equal the number of protons to overall balance the charge for a sum of 0, and therefore we must have 6 electrons. An isotope of carbon 12 is for example, carbon 14, typically used for carbon dating. And so carbon 14 would have its nuclide script as such, with a carbon with a 14 raised to the superscript at the left position. And if we digest this, we recognize that we'd expect the same number of protons, otherwise I would have to switch the identity C to some other element from the periodic table. So we're still going to see 6 here. The number of neutrons, however, is what's going to give me the different isotope here. So I have to have a different number than above. And so the number of neutrons here has to be 14 minus 6 for the 8 now. And of course, we're still going to neutralize this atom for the neutral carbon 14 isotope. And so I have to have the same number of protons. And so here we're going to have total number of electrons equaling 6. Okay. And so if you turn to the periodic table, what the periodic table must do is report the atomic mass, not for every single isotope, but for the average of all isotopes known for the elements in question. So if we turn to the periodic table briefly, and let's look at the carbon area in particular, we see here that carbon is listed here in the second row of the periodic table, and at the 4th sort of position along that row. And we see the number 6 above, so we recognize that. That is the 6th element in the periodic table, so we're seeing the 6 protons reflected there. And then down below, we're seeing that atomic mass, but now presented with a lot of detail in that we see decimal points. Okay, so here what we have is the average AMU value, atomic mass unit value, for a carbon, for the carbon element, and we incorporate all the information about isotopes in here. So there's an average atomic mass here. Okay, so the atomic masses on the periodic table are the average atomic mass. Okay, so let's touch on that. And so what we have here as a follow-up is that the average atomic mass is the weighted average, and I'll put in parentheses, by natural abundance weighted average of the isotopes of the element. So if we consider the element bromine, we'll sketch that here. Br is the symbol for bromine. Br has two major isotopes. Okay, so we see that here. It is the 35th element in the periodic table, so we're expecting 35 protons for the bromine atom. Okay, so that allows me to use the Br abbreviation for bromine. And we can see here that we have 79.904 as the average atomic mass. Okay. S 79.904, and we have that as the 35th element of the periodic table. So bromine has two major isotopes. And we have bromine 79. Sorry, there's 79. Let me correct that. And we have bromine 81. And the abundance for these, the abundance is roughly 50-50, but let me put that with more detail here. The bromine 79 is 50.69% of all bromine. The abundance for the other isotope is the makeup from 100 to that 50.69%. So that would be a value of 49.31%. So because these two values are close to 50 and 50, we can expect that the average atomic mass for all bromine would lie pretty close to the midpoint between 79 and 81. And so you're hopefully seeing here that the midpoint for 79 and 81 is, of course, 80, and we see the outcome in the calculation coming out to be pretty close to 80, 79.904. So how do we determine what is the actual calculation here? The equation will vary depending on the total number of isotopes. So there will be additional terms depending on the total number of isotopes. So typically what's done to calculate the average atomic mass for an element. Sorry, let me touch that up. For an element is we have to sum a series of products. Okay, so the first would be the atomic mass of isotope 1 times the abundance of that isotope. So abundance, and we'll put this here as abundance fraction for isotope 1. Okay, so that product is the first term, and then we have to add this to another term. Add this to the next isotope's equivalent information. So the atomic mass unit of the second isotope times the abundance fraction of isotope 2 plus, and then the pattern would continue according to the total number of isotopes that can be naturally found. Okay, so you may not need the fourth product term shown here if there are only 3 known isotopes for an element. Applying this equation to bromine, you can see here that given that the abundance of bromine 79 is slightly more than that of the bromine 81, we'd expect the average reported on the periodic table to lie closer to the value of that more dominant bromine 79. And so the closer to 51 weight percent or abundance value there shifts that away from 80, as we see reflected in the ultimate average on the periodic table. The equation here helps us with that. Okay. So with that, we should be able to handle an example problem. So let's try that. Okay, so we'll just make some space for that here. Okay, so our example will be the following. Determine the average atomic mass unit value for neon given the following information. Okay, so a little table would be provided. We would have the isotope in question. Okay, so we would have neon 20, neon 21, and neon 22 to comprise the 3 known naturally occurring isotopes for neon. And we would need abundance information. So the percent abundance information here is 90.48, 0.27, and 9.25. Notice that the sum here is 100 to describe all isotopes in totaling to the total population of 100. And that's where we would end the question. So if you followed the logic for the problem from the previous discussion, we know that we will need this new thought, which was the abundance fraction. So we can add that and calculate that quickly. So the abundance fraction must be a value between 0 and 1. Okay, so here you can see quickly we're simply going to divide by 100 from the second column to get the values in the third column. 0.9048, 0.27, and 0.2, add 2 zeros on that, 0.0027, and 0.925. Okay, so that wouldn't be provided. That's part of our solution. We have that now. And we know from our previous equation that the average AMU value for neon has to be a sum of some products. So the first term is going to incorporate values for the AMU value for the one isotope times its abundance fraction. Okay, so we're going to put some values in there, and then we'll add that to the next equivalent product and finish that off with a third set of terms because we have only 3 isotopes here. So the first term was the mass value, the atomic mass value of the isotope. So the 20 value is what we use here. So we know that there are 20 AMU for that particular isotope. And its abundance fraction is unitless now. Notice there's no percentage because we eliminated that by dividing through by 100%. And that fraction amount goes here, 0.9048. You might pause the video at this moment and try to complete the other 2 sets of terms to ensure you know how to do this, and then resume the video once you've done that. Okay, so if you're seeing the pattern, we're going to need 21 AMU for the next term and its abundance fraction, which is going to be 0.0027. And then the final isotope is characterized by an atomic mass specifically for that isotope as 22 AMU. And we have an abundance fraction there of 0.925. So before hammering away on our calculator, we can try to make a prediction. Where should the average value be to try to check our work as we determine that value? Most of the contribution to all the neon comes from the neon 20. Notice the 90.48%. So that is to say almost 90.5% of all neon is the lightest option here. So we would anticipate that the average atomic mass value, average atomic weight for neon that blends in all the properties of all isotopes for atomic weight would lie close to this value of 20. So our answer should be quite close to 20, probably not moving past the 21 value and certainly not reaching close to 22. Okay, so working with those numbers in our equation, we could now move to our calculator and do the calculation. And so we would have 20 times 0.9048 for the first value. That's about 18.096 plus the next one, which would be 21 times 0.0027. And that's 0.0567 added to that first value, plus our final set of terms, which is going to be 22 times 0.925. And we get a value here for our total answer of 20.19 AMU. Okay, and so our prediction was that the value should lie close to the lightest isotope because it was the most dominant by population, representing 90 atom percent of all neon known. And so our value here agrees with that. So hopefully you've been able to see how we've used a general equation here to determine the average atomic mass for a neon. Since there were 3 isotopes here, we needed 3 sets of terms Okay, so 3 isotopes here, demanding 3 sets of products that are summed together. A trick is to ensure that we're using the abundance fraction. This abundance fraction must be between 0 and 1. And we can transform percent abundance information, sometimes known as the atom percentage, for the population of an isotope, for that isotope represented as a fraction for all of the isotope options. And we can transform that percentage into the fraction by dividing by 100%. Okay, so that's a key need there, is to make sure you're using fractional amounts there between 0 and 1. And then we were able to check our work by considering what was the most dominant isotope and anticipating a value close to that, given the weighting of the values by way of that abundance information. Okay, so that's isotopes